People come in late, they need a quiz or something. So, now the next thing, any questions about the homework? I'm gonna give you a couple problems. Any questions at all? They were straightforward? Yes.
Can you go through number 2, please?
All right, and since number 2 is not in front of me, describe it.
So on the left side, you have 4 milliamps.
Current, 4 milliamps.
Yep, and then a switch in parallel that starts open.
Here, like
Yes.
down,
Yeah.
and it starts open, closes at t equals 0.
Yep.
Right.
And then resistor in parallel at 10 ohms.
Get a better marker too. This is 10 ohms.
And then a capacitor in parallel with that.
What value?
It does not give it to
Does C not give us? 1 microhenry? I mean, 1 microfarad. Yeah, I thought it was. C equals 1 microfarad. That's 10 to the minus 6 farads. Micro is 10 to the minus 6. And the question is what? Voltage on the capacitor?
Equation for VFT.
But DFT is across the capacitor?
Across the resistor.
It won't matter. They're the same, right? Isn't the voltage across the capacitor the same as the voltage across the resistor class? How many C's? They're in parallel, right? It doesn't matter which one it is. All right, now to do this, the steps are straightforward. First thing you do is find the voltage, right, before the switch closes. Correct, class? Before the switch transitions. So the VC in this case, voltage on the capacitor for t less than or equal to 0. What would that be? Well, the switch has been open forever, right? Since time began. I have 4 milliamps going there, right? Can any of that 4 milliamps go through the capacitor? Why can't it go through there? In your own words. What does a capacitor look like when there's nothing varying with time? Open circuit, sure. This looks like an open circuit. All the current must flow this way, correct, class? Everybody with me? That means 4 milliamps times 10K is 40 volts. How many see this? Are you with me on this? 40 volts. Now, show of hands. You all see it back there. I don't care if you text. Just give me a little attention here to make sure that you're on the right page with me on this one. So this is 40 volts. Now, the next thing I'm going to do, and the order of this is not important, but for me, the next thing I do is find the voltage on the capacitor as t goes to infinity. All right? All right, when t goes to infinity, what happens? Well, this is closed, right? Isn't that right for t greater than 0? When it's closed, what happens? It literally shorts out all this current. It just flows around here, doesn't it? That and that literally are the same, what? I mean, well, let me do it this way. This is actually a very bad problem. Because you know what happens when that switch closes? Some of you do. It doesn't blow up. When it shuts, it shorts out everything. This problem I took, and do you all see that, class? I'm not going to ask you to, but you all see when this shuts, right? The voltage here, when this goes down, literally this is a short circuit. It doesn't matter what's over here. It's a short circuit, right? I'm glad you asked this. This is good. I just posted that thing from a set that I have. That means this is 0. You all see that? So it's 0 for all time. I mean, it's 40 volts for t less than 0, and it goes to 0. So for t less than 0, it's 40 volts. T equals 0 or greater than 0 is 0. You all see that? How many do? It has to be, because you shorted out. So you can just say it's 40 volts, 0. That's it. No time constant. I apologize if that one, it probably, I think what it meant to have was this. It meant to have another resistor there. And there wasn't a resistor there? Isn't that right? Well, that's a dumb problem. I'll check them better next time. Another question about the homework. Thank you for asking it. Now, I won't do this to you, but I know at least one professor that probably would do something like this. Not to you guys, but to double E's, just to make sure that everyone's sure. Anything else? Did you have another question? Did anybody have another question?
At t equals 0, the switch opens. Does that change? Now the problem solved.
Wasn't it closed at T equals 0? Isn't it closed at T equals 0 or is it open? Well, then it shorts everything out, right?
Oh, they close when the arrow's going the opposite way.
Well, let me see what it says. That's from a bunch of, I thought it was, the problem was right, but let me just check. But the way it was described to me is the way I drew it. It opens at T equals 0. Oh, that close opens at T equals 0. Now that's completely different. I misinterpreted something it said. Let me go here and redraw this. Thank you very much. All right. So we have this. Let's try this a second time. I have 4 milliamps here. Then I have a switch here. And the switch actually opens at T equals 0. And then you have a resistance here of 10K. And then you have a capacitance of 1 microfarad. And they want this voltage. Now I want to say one thing. It doesn't matter if the resistor is over here and the capacitor over here. It doesn't matter because they're in parallel. Absolutely no change. But if we look at this for a second, now the steps are still the same. First, I find the voltage across the capacitor for T less than or equal to 0. What is that going to be? This is closed. It's got to be 0, correct? That's a direct short. Do you follow me? All the current just swirls there at 0 volts. So it's 0 volts. Second part is the voltage across the capacitor as T goes to infinity. Here, I talked about this last time. What does a capacitor look like as time goes to infinity and why? How many know? I'm not going to ask you, how many know? Well, it looks like what? An open circuit because there's no time variation, right? And we know the current through a capacitor, I'll put it up here one last time. When I have a capacitor, the current through the capacitor is equal to C dV dt. Well, as time goes to infinity, there is no change in the voltage with respect to time. Follow me? Therefore, there is no current. No current means open circuit. It looks just like it's disconnected. Do you follow me in that class? Like an infinite resistance. So, when we look at this and it opens, now 4 milliamps is flowing, right? As T goes to infinity, none of that current can flow through there. You follow me? All of it must flow here. You all see that, everyone? If all the current flows there, what's the voltage? 4 milliamps, 10K, 40 volts. So this is 40 volts. Right? Now, after that, we find something called R Thevenin, right? And R Thevenin does what? It literally, and you can do this until you get used to it, just erase the element and put in 2 little dangling leads, and we want to know what the resistance is here. That's R Thevenin. Now, we have to turn off the sources, so when I turn off a current source, what does it become? Class? Open circuit. So how much resistance is between those 2 dangling leads? People? It's just going to be the 10K ohm. Now, the next thing I like to get, the order is unimportant, I do it this way, is going to be the actual time constant tau. And that's R Thevenin times C for RC circuits. Got it? What's that going to be? Well, it's going to be 10 to the minus 6, right, times 10 to the 4th. Do you agree with me? And that's 10 to the minus 2. Do you agree with me, class? How many do? So it's 10 to the minus 2 seconds. Or 1 over 100 seconds if you want. Then we go ahead and we solve the equation. Remember, the general solution for the voltage across the capacitor is some K1 e to the minus t over tau, that tau, plus K2. Remember that? Now, we're going to go ahead and do this. This is really, that's the general solution. Now we use the boundary conditions at t equals 0 and infinity for the specific solution, right? When t goes to infinity, what happens to this term? The k1 e to the minus t over tau. People? What happens then as time goes to infinity? I have e to the minus infinity. What is that? It's 0. That goes away. So K2 is the voltage as t goes to infinity. You all agree with me there? How many see this right here? It's straightforward. And you have to keep up with these, because trust me, when you cram on these things, you'll be so confused you won't know what you're doing. And people fail this course all the time. I hate to say that, even seniors, graduating seniors fail this repeatedly times. I've had a kid fail it twice. All right, this is just going to be equal to K2, which is, in that case, it's going to be a voltage as t goes to infinity, or 40, right? You agree with me there? How many do? Now keep watching. What happens next? I take the voltage as t equals 0. When t equals 0, you see that's just K1 plus 40? How many do? Now think about this. What is the voltage as t equals 0? 0. Remember, I didn't say this strongly enough, I think. Maybe I didn't say it at all. Voltage across a capacitor can't change instantaneously because it's based on an integration of current. It has to gradually change. You don't have 5 volts, 100 volts on a capacitor. That would imply an infinite current. You follow me? What it amounts to is the voltage at t less than 0 has to be the voltage at t greater than 0. We know the voltage at t less than or equal to 0 is 0 volts, right? Now when I put down here 0 is equal to K1 e to, right, so t equals 0, that's just 1 plus 40. How many see that K1 is minus 40? Everybody on me with this? All right. Now, so that means what? Vc of t will be equal to 40, right? And it's going to be 1 minus e to the minus t times 100, if I put in the actual value for tau. And this would be true for t greater than or equal to 0. That would be the solution. Do you all agree with me, class? It's straightforward. It is very straightforward, and it doesn't matter the order you get that information, because it's just applied here. That's all. Got me on that? Any other? Yeah.
Can you go over how you got the units for tau one more time?
Oh, I got what?
Tau, the units for tau.
All right. Tau will be in seconds, because ohms, right, times farads is seconds. And really, I can show you this later, but Google it. I have very smart children, it seems, in my classes at times, and they just, we'll just Google it. I asked somebody that, no, you're supposed to know what. Why yes? All right, you all agree with that? It's 100 times t, because it's 1 over quantity, 1 over 100, or 100 t. Everybody agree with that? Any other questions about the homework problems? I can only give you a few. Y'all do them? I hope you did. Because any other questions? Now I'm going to give you some more capacitor problems today with solutions. But next I'm going to go, now we go into inductors. This stuff is going to come at you fairly fast. We're going to be doing a lot of different elements for transient and steady state. So moving on. The next set of problems I give you be a little harder when it comes to capacitors. More different. How many went to the game? How many almost burned up? I don't know what the temperature on the field was. All right. Next. Now we're going to talk about inductors. Write this down. When we talk about an inductor, you've had it in physics, you've probably seen it in some of your other classes too. The symbol we use for an inductor is just, it looks like a coil of wire. That's an inductor. The actual symbol is L. The units of inductance are henries. But they're abbreviated just H. Now, the relationship between voltage and current in an inductor is that if this is the voltage across the inductor, and this is the current into the inductor, it says that L times di of t dt, the change, is equal to V on the inductor of t. So it takes a time-varying current to get a voltage across an inductor. Do you follow me on this? Now what that also implies, without me ever stating it, is if the voltage doesn't change in time, suppose you put 10 volts across it. I'm sorry. If the current doesn't change in time, let me do it backwards. If the current is just 5 amps, follow me? Constant, there is no voltage. What is an inductor? Probably the best way to think about it, from physics, you remember this? It's just a coil of wire. The thing that makes an inductor work is the storing and then really recovery of magnetic energy. It's stored in an inductor. A capacitor stores electrostatic energy in a field. An inductor causes a magnetic field that stores the energy. So on the inductor, in some senses, is an energy storage device. That is the relationship between voltage and current in an inductor. Now this is important that you see this. When di dt equals 0, V of t equals 0. That's very important. When nothing's changing, the voltage across an inductor is 0. And a voltage in the actual inductor itself looks like a short circuit when nothing's changing. All right? So here's how we do these problems. When you have this, before when we had a capacitor, we got the voltage across the capacitor, right? With an inductor, it's the exact opposite. What we do is find the current in the inductor for t less than or equal to 0, or really where the transition begins. If it was 1 second is where something switched, then you would go from t equals less than 1 second or t greater than 1 second. Follow me? Now, we find this value. Then we find the value of the current through the inductor as t goes to infinity. Very similar to what? Before it was just voltage at those 2 points, right? And then we find our Thevenin by turning off the switches and seeing what actual value of resistance is between the terminals of when the inductors are removed. You follow me? Just like we remove the capacitor, here we remove the inductor. I'll be doing several problems to make sure you get this. With me? Then we find something called a time constant, tau. But now tau is equal to, you're going to see this is going to be L divided by R. And give me 1 second. I'm just checking on one single thing. We're not going to use second order circuits at all. This is what tau is in this one. was taking a look at something else in the book. And then you put this together, you put I through the inductor as a function of t is k1 e to the minus t over tau. That's the tau plus k2. Now, I'll make mention of this. I'm going to do some problems, but I want you to listen to me. This value of K2 is associated with the current flowing in the inductor as t goes to infinity. Can you all see this from the equation? Because as t goes to infinity, this term goes to 0. Following? Now, the current at t equals 0 is not equal to K1. It's equal to K1 plus K2 is the current at t equals 0. You all see that because at t equals 0, e to the 0 is 1. Common mistake is they'll just put in that current there. It's wrong in general. If there is a current at t equals infinity. The time constant is the critical thing. Now I'm going to do several problems related to this to try to expose how you do these things. It's really through working problems you get an understanding of this stuff, in my opinion. So now, I want to leave that up there. I was trying to figure out how they taught this in physics, and I'm really not sure if they did solutions of differential equations for second order with you guys or not in physics, because I don't actually know. All right. The problems that I gave you were not out of this book. I had a lot of different problems. This one. All right, let's go do this one. So we're going to have 30 volts. Then we're going to have a resistance of 2 ohms. Oops. Then a switch that opens at t equal to 0. Then, oh, this is going to be fun. Then 6 ohms. And then they have 2 Henry inductors. So there's my inductor, and it's 2 Henrys. And then they have 4 ohms. Oh, I like this problem. It's got something that will cause people to make mistakes if they're not attentive. And 6 ohms. And what they want is this current. They're looking for the current through that element. All right. Let me erase this. Actually, let me just put that there because we can fill this in. Now, follow me, class. T less than 0, this switch is closed. Y'all follow me? Now, they want this, but let me give you a piece of advice. You don't care about that right now. The only thing you care about is this. Just show that and say, I want IL of t. That's what I care about. I want the current through the inductor. It doesn't matter if they want a voltage or a current somewhere else in the circuit. That's where you're going. Are you with me, everyone? Now, how do you get it? You start out by finding the current in the inductor for t less than 0. Now, here's where you listen. That switch has been on since the beginning of time. It opens at t equals 0. Follow me? What does an inductor look like when nothing's changing? Short wire, whatever you want to call it. So I'm literally going to put it in. I'll put the inductor back in a second. But this literally looks like that. You agree with me? Now, how much current flows through there? Well, I'm going to suggest something to you. If you want the current flowing through there, there's a lot of different ways we can get it. What this circuit reduces to, and I'll put it right here, is 30 volts with 2 ohms. 2 ohms. And then I have 6 ohms here. And I have 10 ohms here, right? And I care about this current, right? Y'all see this? Can you see it in the back, guys? Okay. Now, hear me. Couldn't I say that I could get a series, or I could get a parallel resistance here, add it to 2 and divide it into 30? Do you all agree with me? And that would be the current through here. And then once I had the current through there, I could say through current division, the current through here would be that current times 10 over 10 plus 6. Do y'all agree with that? You can do it that way. A second, I'm going to just tell you what your choices are. A second way is I could do a source transform here, couldn't I? And I could say that this right here really looks like 15. Right there would be 30 by 2 is 15 amps, right? And then 2 would be in parallel with it. And then 6 would be in parallel with it. And then 10 would be in parallel with it, right? Agree, class? And what I could do is combine the 2 and the 10 to a single resistance. Do you agree? And then I could do current division. How many see this right here? We'll go this route for now. I'm just showing you your options. There is no right way. It's many ways. Now, if I do, and I could also do one other thing. I'm thinking about everything. I could remove that, and I could find the open circuit voltage, and then I could find the Thevenin equivalent resistance, and then I could plug it back in again. Do you all agree with that? That would be Thevenin's theorem being used there. And it doesn't matter how you get it. Just know how to get it. Because I'm not going to say get it one way. You can get it any way you want. Just get the right answer. So for this, what I'm going to do is take this, and the 10 and the 2 and make a single, all right? So what would that be? It would be 2 times 10 or 20 divided by 2 plus 10 or 12. So 20 by 12, 10 by 6, right? What? 5 by what? 3, right? So what I could say is, erase this one, make this 5/3, right? Of an ohm. You all agree with me there? Now, to get the current through here, what is it? That current, I through the 6, which is my I for t less than 0, or equal to 0, that would be equal to that current, 15, right? Then it's divided by the opposite resistance, which is 5/3, right? Divided by what? The sum of these. So it's 6 plus 5/3, right? Do y'all agree with me there? Class? How many see this right here? Okay. Y'all see it or not, really? See it? All right. Once you got that, what can you do? Well, 6 is really what? 18/3, isn't it? 18, y'all with me on this? And what we could, I mean, it's up to you, but what do you get for this number, someone? So that's, what do we got? 15 by 3, 25. Just give that to me, someone. Let's see, 18. What's the number?
75.
Just a single number. I mean, say again?
3.26.
Thank you. 3.26 amps, right there. All right. Now, so that didn't turn out. I was hoping for an easy 3.26 amps. Now, what is the current as t goes to infinity? I'm going to show you something on this one. I'm going to put the inductor back in so you can see it. It's 2 henries, right? Now, as for t greater than 0, or as t goes to infinity, this thing's open, isn't it, class? Now, what is the current going to be as t goes to infinity? Give me a reason, in your own words. How many see it's 0? Why is it 0? You're right. There's no source of energy to sustain it, right? There's no battery, no current source. If there is no source in the circuit for t greater than 0, everything decays to 0 if there's a closed path for current. And that means this will go to 0. So that means this is 0, which is nice. Now, the next thing we need is R Thevenin, and that's the value of the Thevenin resistance across the inductor. So what I do, does everybody follow me so far? So, yes?
What's that multiplying after the equal sign?
Here?
Yes, after that, what's that?
This is the resistance, the opposite resistance, which is 5/3, over the sum of these two, 5/3 and 6, times the actual current 15. Y'all see it?
I was talking about the number, but it's 15.
Yeah, what, this?
No.
What?
He's talking about the 15.
That you're multiplying times.
That's 15. 15 is not a good 15. Sorry. All right, now we got to get R Thevenin. So what I'm going to do literally, and I like this approach, The switch is open, I remove that, I want R7 to cross these. What is R7? Can you all see they're all in series? Can you all see by looking at that, that's 16 ohms? Right? So that's 16 ohms. Finally, what is L over R? One over 8. Do you agree with me, class? 2 over 16, that's L divided by R, or 1 over 8. Everybody follow me on this one? Try to do this very slowly the first time. We'll go through it a little faster as we get going. Now, finally, we've got to do this final form of the equation. I'm going to give you a second to catch up with me. Make sure you see this. We'll get this done. So what happens here? Guys? Well, what is K2? Look.
0.
It's the current as t goes to infinity, right? Isn't that at K2? What's the current value as t goes to infinity? Can everybody read that? It's 0, right? So it goes away. That's a nice thing. Makes my life even easier. Now, what's the current at t equals 0? 3.26, correct, class? Now, what is that? That's this for sure, right? Because t equals 0, e to the 0 is 1. That has to be that, doesn't it, class? How many see this? So I know for a fact that IL of t now is equal to 3.26 e to the minus 8t amps. And the reason it's minus 8t is because tau is 1/8, and it's e to the minus t over tau. So 1 over 1/8 is 8t. Agreed, class? All right, now I've got that for the current, but that wasn't the current I wanted. I got that current, right? For t greater than 0. What current did I want? Tell me about this current that I want in the current through the inductor. Anything. Are they the same magnitude? Yes, right? But what? This is negative of this, isn't it, class? If I say I got 5 amps going that way, I have minus 5 amps in that direction. Do you all see that, class? So the actual current that I'm looking for, the I of t in the problem state would be minus 3.26 e to the minus 8t amps. And that's it. That's how you do it. Now, we'll do some more. Then you'll get the hang of this.
Just real quick, you sort of switched your notation of the current to a lowercase I for doing these problems. There, real reason.
I don't care which one you use, but lowercase usually means time delay. If you're at a constant frequency or DC, it's capital letters, but it doesn't matter to me. Yeah.
Can you explain that last part again where you got the negative?
All right, now we have this current right here, right? I want to make sure you understand it. This part of the circuit's disconnected. It's like it doesn't exist, right? So this current flowing this way is positive. You see, if I wanted the current flowing this way, it would just be minus that.
Okay.
5 amps this way is really minus 5
Oh, I see the
amps.
current. Okay. That makes sense.
Yeah. Are you with me, everyone? Yeah. Speak up. What?
It's a K2.
K2, well, K2 is the current as t goes to infinity, right? What is that value? 0. That's the reason K2 got erased. Because K2 is 0. Okay? Because the current here as t goes to infinity is 0, and that's what K2 represents, the current as t goes to infinity. Got me on that one? Everybody? How many see this right here? I mean, I've got to make sure. All right. I mean, I hope you do, because it parallels exactly what we did with the capacitor, only now we talk about current instead of voltage. Same thing. We're going to do a few more.
Before we go on, just want to let you know that we said we would go down our testing.
Thank you.
Yeah.
Done. Just when I was getting warmed up. Thank you. I appreciate it. All right.
Sounds like bubble wrap. Sounds like a
It really can't be next week because we need to cover another bit. Well, I guess it could, but I prefer it not next week. If you want it next week, I'll give it to you. So give me some test date possibilities.
2 weeks or a week from Monday.
Give me a date and
2
a
weeks from
day of the
Monday.
week.
What is a week from this Monday?
Monday.
Hold on. You want, let me just do it this way. Monday, Wednesday, Friday. This is the 23rd, is this right? 25th? And 27th, all right? Is that week good for people?
Yeah, that's it.
All right. Now, one last statement, then you pick, I don't care. If you, Monday tests usually on average have the highest score, highest average scores. Friday tests the lowest, typically. But, I mean, you know, what's typical generally is not maybe typical for you. Yes, sir?
Yeah, I was just wondering if it's the idea to decide test day next week.
We can debate that, but I think I said today, and I think, is everybody all right with today?
Yeah.
If you are, show of hands, because I want to make sure what I'm doing here is.
No, debating if today is a good day to pick the test.
Is it all right if we vote on it today or not? We're not having a test today, at least. All right.
10 minutes.
Hey guys, here's the way it works, all right? I'm gonna ask for show of hands, and then I'm gonna have somebody else count with me. That would be you. And you. So you two count with me so I don't make a mistake, because I'm old. Now, if you want it on Monday, one hand high. Hold.
Well,
I'm just going to make a suggestion. I think is it unanimous? Does anybody have any concerns that that's unanimous? Well, soon.
Let's go.
I actually had a professor one time said this to me, and it always stuck with me. Yes, sir.
So you said your statistics are come out to where Monday tests have the highest test average, but do you know if that is, if Monday was the last day that they had the option to take the test? You know what I mean?
I have no clue about that. I'm just telling you what happened from 30 plus years of teaching. I have watched this, done statistics on it, is unbelievable. It's usually more than 10 point difference. Actually, it's probably about close to 15-point difference on average of test scores, and this is out of 100, at least. Yeah. I don't care about what you think. This is the test date, period. Every day could be a little bit better, but this is the test date, Monday, the 23rd. Everybody got that? All right. Can somebody send me an email? Somebody post it on that group thing. All right? It's your thing, so you post it. Put it in big flashing lights. You too, yeah. Post it. I don't know if you've noticed this, but I'm going to tell you, Friday tests are nightmares. Usually people have, I don't know what goes on now. Lab reports used to be due Friday in a lot of classes. You'd have 3 reports to do for 3 different laboratories, and you're up all night, and then you got a test, and it's like, hey. All right. Just work with me here. You can learn a lot here just listening and working with me, because it'll save you some trouble. The next problem is this one. I'm going to take 12 amps here. All right. For this problem, this is an easy one too. The next one after this one won't be so easy. For this problem right here, now take a look. First thing I usually get is the current through the inductor at T for T less than or equal to 0. Now take a look at that First, what does an inductor look like for t less than or equal to 0? Class? Short circuit a wire, right? Because there's nothing changing with time. Do you all follow me on that? So if that's a wire here, I'll even make it a wire. And I want that current right there, t less than 0. What's it going to be? Now take a look at this, people. Nothing flows through that switch. All that current flows through there. Isn't that right? All that current hits this juncture and then it divides. Isn't that right, class? You all see that? How much flows this way? Well, that amount of current would be equal to the total current, 12. Then it would be times the opposite resistance, 3, divided by the sum of the resistances, or 9. Can everybody see that, class? Or what would it be? 1/3 times 12, or 4 amps. Isn't that right? How many see this, right? Y'all see it, class? Give me a show of hands if you do. I want to make darn sure that you can see this. That's simple current division, right? That 2 ohm resistor there doesn't do a thing. It complicates the problem a little in a second, but it doesn't do a thing to this. Now, that's where the inductor was. I'm going to put it back in, and that was 2 henries, wasn't it, class? Now, right here, when the switch closes, listen to me. When the switch closes, that's a direct short circuit, isn't it, class? So this thing's basically out of the circuit. So for t greater than 0, we're left with this. Can you all see that, class? Everybody? Now, what is the current in the inductor as t equals infinity? 0. Very good. And it's 0, and you're going to hang of it because there are no sources for starters. There's nothing to sustain it, correct? It's going to decay to 0. Can everybody see that in the back especially? You must have eagle eyes if you can sit that far back and read my writing. All right, now we need the resistance, R Thevenin. Correct, class? For R Thevenin, this is important to see this. I'm going to erase that inductor and just put in some dangling leads. I want the resistance between those 2 terminals. I literally rip the inductor out. I want the resistance across the inductor. Follow me? Well, what's it going to be? Well, it's going to be at least 6, right? Right? But what? Isn't that in parallel with that? So 2 in parallel with 3 is what? 6/5, isn't it? 6/5 of an ohm. See, these numbers aren't working as nice as you'd like it to be. 6/5 of an ohm plus 6 ohms, right? So I have 6/5 of an ohm plus 6, and
36.
that's 36/5, right? Of an ohm, whatever that is. Do you agree with me, class? With me? Now we need tau. What is tau? L over R, correct? Hear me? People mess that up until you do it enough times, you won't.
What is that, 5/6?
It's 36/5 total. 5/6. If you have 2 in parallel with 3, it's what? 2 times 3 is 6. Over 2 plus 3 is 5. It's 6/5. Correct, class? All right. Now, if I look here, L over R, well, L was what? 2? Is that right? So it's 2 over 36/5, or really 5 over 18 seconds. Correct, class? And then, what do? Well, then I go, every time I see you looking at your watch, it's all right, I'm off. It's all right. Now, what do? I'm going to go ahead and write the general equation. And I know that IL of T, this is my inductor, this is the current I'm getting, is going to be equal to K1 e to the minus T over tau plus K2. What is K2, class? By this time, I think you're catching it. K2 is the current as T goes to infinity, which is 0, correct? How many see that right there? Got it? If you can't see, just move on down. If the current through the inductor is 0 as T goes to infinity, just erase K2. Leave it hang on. You don't need it. Now the next thing, what do? Well, I need to find out what K1 is, right? So I evaluate the current ST, what? For T less than or equal to 0. And by the way, current through an inductor cannot change instantaneously. It can't go from 0 to 50 amps, or it would imply an infinite voltage. There has to be a continuum. There can't be a discontinuity. So based on that, the current for T less than 0 is the current for T greater than 0. What is the current at T equals 0? 4 amps, right? 4 amps equals K1 e to the 0, or K1 is 4 amps. You agree with me? That's 4 amps. E to the minus t, and I know the time constant is going to be equal to 5/18 of a second. That's it. That's for the current through the inductor. And that's it. Now, question for you. What if I wanted the voltage across here? What would I do? I got the current, don't I? Multiply it by the current. Multiply the resistance by the current. You got voltage, correct, class? That's the way you think of these things. And again, what the thing you're after is the current through the inductor. Now, there are problems. I'm about out of time, but I'm going to tell you there are problems that I'm going to give you, and I'll give you solutions. Some more difficult capacitor problems and some inductor problems that have some more difficult ones in it. And next time we're going to go ahead and just bludgeon them to death, but try them. I want you to make sure you really make an effort to try these, or else when I show you how to do them, I will not answer the questions that you've already developed in your head. So you develop questions, and you come to class, and I can answer them. Usually you don't need to relearn that material.